All right, welcome back. We've completed our videos on how to do Lewis dot diagrams and how to draw them. We've looked at a couple examples. So now we're going to move on to what's called formal charge. So what is formal charge? It's kind of an electron locating bookkeeping, I guess if you will, figuring out where all the electrons are. Simplistically, what it is that it's a way of helping us determine what the best structure is for a Lewis dot diagram. So that's the most simplistic way I can explain it, and you'll see why when we start doing some examples. So in order to figure out formal charge and what the best structure is, we need a way to calculate it, and it's real simple. The equation to figure out formal charge is you're going to take the number of valence electrons for a particular atom, and you're going to subtract from it the number of associated electrons. And I'll talk about what that means. So formal charge is not something that is assigned to a molecule, it's something that is assigned to every atom in a molecule or ion. So it's something you will actually assign to every single atom. So let's take a look at an example. Ozone. So what we're going to do is we are going to do a little bit of practice once again with our Lewis dot diagram. So we're going to have to draw the diagram, and then once we draw the diagram, we'll then assign formal charges. So we have O3. So O3 is ozone. And O3 it's just three oxygens bonded together. So oxygen 1, oxygen 2, and oxygen 3. So oxygen is both a central and a terminal. And it's bonded just like that. It's bonded in a, I'm not going to say a word linear because that's not correct and you'll understand once you do molecular geometry. But it's basically just in a row. So it's not like a triangle or anything like that. Okay, so same thing as before. Let's count up our number of valence electrons. Oxygen is 6. There are 3 of them, so we have 18 electrons at our disposal. Single bonds to the terminal oxygens to the central. I just used 4, so that means I have 14 valence electrons left over. Satisfy the outside oxygens first. 2, 4, 6. Whoops, got a little crazy. Hold on. Hold on. Try that again. Where's my pen? There it is. Okay, there we go. 2, 4, 6. 8. 10 and 12. All right. I have 2 left over because that was only 12. Regardless of how many I have left over, I stick them on the central and then you stick them in pairs. So now I am done. I have 0 left over. The oxygen in the middle, however, is not happy. It only has 6. So I need to do a double bond. It does not matter what oxygen I choose. I'm going to choose the one on the left. It's just out of habit. I always seem to want to erase part of the element when I do things like that. There we go. All right, so I moved those 2 electrons in the double bond. Okay, so there is the Lewis dot diagram for ozone. Notice that we have 18 valence electrons in the structure, and all the oxygens are happy. All their octets are satisfied. Now, just for those students that may be noticing, this molecule does have what is called resonance. We have not talked about resonance yet, but just in case you were looking at that, it does. If you have no idea what I'm talking about, it's okay. We're going to talk about resonance in the next video. But for right now, this is the Lewis dot diagram. It is a successful one. We're going to move on. Because now what we're going to do is we are going to determine what is the formal charge on each of those oxygens in that molecule. So here's what we're going to do. We're going to take the number of valence electrons and subtract from it the number of associated electrons. So let's do it for the first oxygen right here. Okay, how many valence electrons does oxygen have? And this is strictly just where it is on the periodic table. So how many valence electrons does oxygen have? 6. So I'm going to do 6 minus, now how many electrons are associated to this oxygen on the left? And here's what I mean by that. You can think about it 2 ways. Here's the first way. How many electrons does this oxygen quote-unquote own? It owns 1, 2, 3, 4. So those 4 electrons that come from those lone pairs, that oxygen owns them, if you want to think about it that way. But then also, these electrons in the middle are half owned by this oxygen on the left and half owned by this oxygen on the right. So you can say this oxygen on the left owns half of them. So it owns these 4, and then out of these 4 electrons that are in the middle, it owns half, so 2. So total, there are 6 electrons that are associated to that oxygen. Now, if that was confusing to you, and probably it's going to be confusing maybe for a little bit, it'll make sense, I promise. Here's another way you can think about it. How many things are touching that oxygen? You've got 4 dots and 2 lines. So total, you have 6 things touching that oxygen. So that's 6, that represents 6 associated electrons. That's another way you can think about it. It's an easier way. It's certainly less scientific, so if you're ever asked to explain that, don't say there's 6 things touching it. But as far as counting up associated electrons, that'll work. So what do we get when you do 6 minus 6? That is 0. And so what that means is this oxygen on the left has a formal charge of 0. So we're going to leave it blank. When it's 0, you just don't do anything. It's assumed to be 0 if you don't write anything. So let's do the oxygen that's in the center. Once again, it's oxygen, so it has 6 valence electrons, minus how many electrons are associated to that oxygen. Well, it owns these 2, it owns 1 of these electrons, and it owns 2 of these electrons. Another way of thinking of it, how many things are touching that oxygen? 2 dots, 3 lines total. That's 5 things. So 6 minus 5 associated electrons, that means it's going to be positive 1. So that oxygen that's in the center has a positive 1 formal charge. The way we show that is we show the charge with a circle around it. Notice I don't write the number 1, it's assumed to be a 1. Alright, let's do the last oxygen here. 6 electrons, because it's oxygen, because oxygen has 6 valence electrons, minus how many things are touching that oxygen? There are 7 things, which means 7 associated electrons. 6 minus 7, negative 1. I need to show that by doing the negative with a circle around it. That oxygen has a negative 1 formal charge. Here's the last step. The total of all of your formal charges should equal the total charge of the molecule. Ozone is a neutral molecule, so all the formal charges should add up to be 0. And they do. Positive 1 and negative 1 cancels out to be 0. Okay, I'm going to show you something that is going to help save you a lot of time. Oxygen is probably the most common terminal atom you're going to see. It pops up so many times. When oxygen is in the terminal position, meaning it's in the outside position, remember I said oxygen favors double bonds when it's in the outside position? Why is that? Because when oxygen is in the terminal position and it has a double bond, its formal charge is 0. If oxygen is in the terminal position and it is singly bonded, which is going to be a common thing, you'll see it quite a bit, it will always have a negative 1 formal charge. Always. And that's going to save you a lot of time if you just remember that. So let's look at another example. Let's look at nitrate. First thing I want you to do, pause this video and draw the Lewis dot diagram for nitrate. Then hit play to resume and we'll talk about formal charge. Alright, so here's your valid Lewis dot diagram for the nitrate ion. Remember, it's an ion and needs to have brackets around it with the overall charge of the ion on the outside. So nothing with formal charges yet, that's just the Lewis dot. Okay, now we need to assign formal charges to this ion. There are 4 atoms, so we need to assign 4 formal charges. Now notice, what are the terminal atoms? They're all oxygens, aren't they? Like I said, very common. You're going to see it a lot. Okay, so remember, when oxygen is in the terminal position and it has a double bond, what's the formal charge? 0. It'll always be 0 if it's terminal with a double bond. So I don't have to write anything. When oxygens are in the terminal positions and they have single bonds, what's the formal charge? Negative 1. And so I don't even have to do that equation like I showed you. You can, like, so for example, real quick, let me just do one just so you can know that I'm not steering you wrong. Oxygen has 6 valence electrons minus how many things are touching this oxygen? 6 dots, 1 line. So that's 7 total. So 6 minus 7 is negative 1. So I don't need to show that math every time because I know when oxygen is the terminal position, and it's single bonded, it's negative 1. So the only one we really have to calculate because it's new to us is the nitrogen. So nitrogen here in the center, let's figure out what that formal charge would be. How many valence electrons does nitrogen have? It's group 5A, so it has 5 valence electrons. Minus, how many things are touching that nitrogen? 4 lines. 1, 2, 3, 4. So 4 associated electrons. 5 minus 4 is positive 1. So nitrogen has a positive formal charge. What do all the formal charges add up to be? Well, this positive and one of these negatives cancel out to be 0, and so you have a net negative 1. And look at that. The ion's charge is negative 1. So I know that it's correct. So how do all these formal charges really help us? Well, here are the rules for formal charges. Lewis structures where all formal charges are 0 is preferred. If all the atoms can have a formal charge of 0, that's the best possible situation. However, sometimes that is not possible. For example, with this last example with nitrate, there was no way every atom could be 0 because the overall charge is -1. So sometimes having formal charges is inevitable. So in that case, having small formal charges like +1 or -1 are better and more preferred than having large formal charges like +2 -2 or +3 -3. Finally, and this rule, I want you to star it, highlight it, whatever, because it often gets forgotten. The best arrangements are the ones that have the more electronegative atoms containing the more negative formal charge. And I'll remind you of that. I'm pretty sure I have an example of that too. But I'll remind you of that because sometimes you have possible Lewis structures and you're like, I don't know which one's the best. Make sure the most electronegative element has the most negative formal charge. That's an important rule. Okay, so back in, I think the last video, we looked at carbon dioxide, and I drew the Lewis structure for carbon dioxide for both possibilities, and I have that shown here. So remember I said both of these Lewis structures are valid. You have the right number of valence electrons. It should have, 16? Yeah. And all the octets are satisfied. So both Lewis dot structures for CO2 that you see on the screen here are valid. However, one of them is better than the other, and the only way you're going to know is by formal charges. So let's take a look at which one of these would be more preferred. Okay, so let's look at this first one on the left. We need to assign formal charges to every single atom. So the oxygen that's right here on the left, 6 valence electrons minus, there are 5 things touching it, so that's a +1. So I'm going to write that formal charge right there. Carbon has 4 valence electrons, minus, there are 4 things touching it, so 4 associated, so that's 0, that's good. And then this oxygen right here, 6 valence electrons minus 7 things touching it, 6 dots in one line. Or you can just remember that oxygen in the terminal position with a single bond, that's always going to be -1. So there's the formal charges. So you have positive formal charge on this first oxygen, negative formal charge on the second. All right, not too bad. Low formal charges, that's good. But let's take a look at the second right here. Notice oxygens are terminal and they both have double bonds. Remember, double bonds means a 0 formal charge for both of those oxygens. And if you don't believe me, 6 is the valence electrons minus, there are 6 things touching that oxygen. So that's 6 minus 6 is 0. Same thing for the one over here. So that's good. Carbon has 4 valence electrons minus, there are 4 lines, and so that also is 0. So the structure on the right has all the formal charges of equal to 0. That's what makes this structure better than this structure over here. All right, so let's do a check for understanding. What I would like you to do is pause the video, draw the Lewis dot structures for both of these species here. You've got ions, and then I want you to assign formal charges to every atom in that structure. So pause the video and then hit play to resume. Okay, so I have the Lewis dot structures for these ions on the screen. I haven't drawn the formal charges yet because I'd like to walk through that together. So the first one is fairly straightforward. You should have a double bond between one of the oxygens and carbon. Once again, stressing that it doesn't matter which oxygen that you do the double bond, because once again, this would have resonance for those that are aware of that. And so you could have done the double bond here in the middle. You could have done it over here. I just chose the one on the left for now. So once again, oxygen, very common terminal atom. So when oxygen is in the terminal position double bonded, it's going to be 0. When oxygens are in the terminal position single bonded, those are going to be -1. Okay, so -1, -1. Carbon, 4 valence electrons minus, there are 4 things touching this carbon, and so 4 associated electrons, that's going to be 0. And so the only formal charges here are the 2 negatives right here. And if you think about it, these 2 negatives will add up to be the total -2, which is the carbonate charge overall. So that would be the answer for that one there. Now this second one, I like this one a lot, and I actually apologize because the central atom may have been not as clear. A lot of you may have thought nitrogen was the central atom. Remember, carbon is a common central atom. Also, it's the least electronegative, so it should be the central atom. So even though the way I wrote it, nitrogen looks like it's the central atom, it's actually carbon. So I apologize for leading you astray there. I hope that didn't cause too much angst. But nevertheless, I have 3 Lewis dot diagrams that are all successful Lewis dot diagrams. So if you count up the number of valence electrons, there are 16 valence electrons that are in this ion. All 3 of the Lewis dot structures that I drew, if you count up the number of electrons, there's 16. Also, if you take a look at every atom in all of those 3 Lewis dot diagrams, all of the atoms' octet rules are satisfied. So I have drawn 3 successful Lewis dot structures for this particular ion. However, out of those 3, one of those is better than the other 2. And how are you going to know which one is which? Because of formal charges. So let's go through. Okay, in this first Lewis dot right here, nitrogen, let's figure out what that would be. Nitrogen has 5 valence electrons, minus there are 7 things touching it. Okay, so 5 minus 7, that's going to be a negative 2. Already I'm thinking that's not very good, but nevertheless, there it is. Carbon, 4 valence electrons, minus there are 4 things touching it. That's going to be 0. That's pretty good. And finally, oxygen. Oxygen, it's in the terminal position, has a triple bond. That's kind of new to us, right? So 6 valence electrons for oxygen, minus there are 5 things touching this oxygen. So 5 associated electrons. That's going to be positive 1. So positive formal charge there. Negative 2 plus positive 1, that does give us an overall negative, so I know I did that right. Okay. Not the best. This negative 2 kind of freaks me out a little bit. That's kind of high, but nevertheless, let's just see. Okay, so that's the first one. Let's take a look at the second one. Okay, so nitrogen has 5 valence electrons, but now this time there are 6 things touching this nitrogen. So 5 minus 6, okay, that's a negative 1. That's a lot better than negative 2, so it looks like we're getting better. Carbon still has 4 things touching it, so it's still going to be 0. Oxygen. Oh, oxygen is in the terminal position with a double bond, and that means a 0 formal charge, right? So this structure is a lot better than the first structure, because not only do we have a lower formal charge on nitrogen, it's negative 1 instead of negative 2, but the other 2 atoms are 0. So already I'm liking this structure a lot better than the first one. But we still have one more structure to figure out. Okay, so let me get rid of this up here. Okay, so now nitrogen's formal charge, let's look at this one. Nitrogen has 5 valence electrons, minus down here it has 5 things touching. So 5 minus 5 is 0. Well, that looks good. Carbon still has 4 things touching it, so that's still going to be 0 formal charge. And then remember, when oxygen is terminal and it has a single bond, that's going to be negative 1. Okay, so I want you to compare now these two right here. All right. Both of them have 2 atoms that are 0 and 1 atom that's negative 1. The question is, which one's better? This is where I want you to remember that rule that I said a lot of times students forget about. So if I go back, this one right here. Okay, so it says, oh, I don't know why that's there. Okay, so it says the best arrangements are where, oh, is it freaking out on me? It's freaking out on me. Sorry, everyone. PowerPoint, it's getting crazy. Okay. Best arrangements, there we go. I just wanted to build suspense. Best arrangements are where the more electronegative atom has the more negative formal charge. So, sweet, it saved all my writing, good. So, which element is more electronegative, nitrogen or oxygen? Oxygen is, and so oxygen should have the more negative formal charge. So compare this one to this one, the best structure is actually this third one. This is the best structure because oxygen should be the more negative element in the drawing. So that's where that rule is going to come into play when you have situations like that. So this concludes formal charge. The next section we're going to get into is resonance, and that'll be the next video.